Thank you very much for the nice introduction. I hope you are hearing me and you're seeing me. So today I'm going to be talking about my research on humanoid robotics, and I try to actually guide you a bit through the state of the art and share my thought about, okay, is the humanoid really a hype or actually it's a reality? So I'm gonna give you a bit of visual introduction of what Guillermo just went through. So just to see who I am and from what background I'm looking at the problems, right? So from 2012 and 15, basically I was back in Iran in this, we built this humanoid robot, and then I was the main person behind the control and planning for this robot. So at the moment, we were mostly working on basically classical planning and control method for robots. 2016, I joined Max Planck Institute in Tübingen, and there basically I worked on building this open source store controlled robot and controlling them, both quadruped and biped, and mostly in terms of theoretical work, I was focusing on optimal control. And since 2018, I just shifted some of my basically research toward machine learning, in particular trying to basically combine model-based and data-driven control. So this is a very quick visual introduction of myself. Now, I'm sure most of you have seen these beautiful videos out there. Every day we see a new video, which is quite impressive what humanoid robots can do nowadays, especially entering these professional teams like Unitree and Boston Dynamics, focusing fully on humanoid. We see these kind of impressive behaviors, right? But I would like to a bit push back and say that, okay, these are very nice, showing the hardware is super powerful, but at the same time, we don't want the robot humanoids to do this kind of stuff. Instead, we need to do manipulation in order to be useful. On the other hand, I'm sure most of you have seen the recent advances in foundation model for manipulation. They unlocked many features that for a long time have seemed very difficult. For instance, on the top video, you see that the robot is doing very fine contact reach manipulations, or in the bottom, the robot can reason about the environment and perform a very long horizon problem, getting only a language instruction, right? So this is very nice, but just to give you a bit of overview what's inside these models. So basically, there are two major lines of work here. One is called Vision Language Action Model, VLAs. So here is a picture I took from the Pi 0.5 paper. So the general idea is that you would pick a pre-trained vision language model, as you see on the left, right? So it doesn't have to be a very big model. Normally, it's just something like 3 billion parameter or something like this, right? So compared to a ChatGPT, it's much less, right? And then you use it for two main tasks. One is to basically ask them the pre-trained VLM to basically break down a very high level command like clean the kitchen to something like put the plate in the sink. And also you use it for visual question answering. So you show it the picture and you ask it to describe it. And for instance, the answer is a dog catches a frisbee. So this is trained on the internet. So you just pick it pre-trained on the internet. The key here is the right part of the figure, which you connect something that is called an action head to this VLM. So this VLM breaks down the complex long horizon task to some sub-goals. And then basically you need to map these sub-goals to the actions of the robot. And this is what action head does. And normally what you do here is that you use something like some flow matching or diffusion models. You do a lot of teleoperation on the real robot, collect data and train that. And then you connect these two together, and then maybe you fine-tune a bit on both of them, and then you run it on the system. So the general recipe is something like this. You pick a pre-trained vision language model, and if you want, you can fine-tune them on some scenes of robotic systems, right? Then the second step is the key, where you train a multimodal action model from teleoperation. So teleoperation, again, here is the keyword. So basically, human shows the robot how to do the task. They basically provide a lot of robot motions, and then basically we train the action head. Then, as I said, you can train both models together in the third step. But what happens is that when you deploy them in the real world, normally there are some corner or failure cases. What people do nowadays is that simply they collect more data on those corner cases, add it to the data set, fine-tune it again until it works, right? So this is the procedure at the moment for this VLAs. Recently, there is people are talking about word action models, which is as a replacement for VLAs. But I would say that the underlying procedure is very similar. So the main difference is that instead of using a VLM as the backbone, pre-trained VLM, what you do is that you use a pre-trained diffusion transformer as a video generation module. And on the left, you take this diffusion transformer, and now again you use teleoperation data. And what you do is that you just do joint flow matching on the action and the state as input of this model. So action, if you see, is both the input and output of this model. And on the right, in the inference time, what you do is that you do not have action as input, because action you want it as output. What you do is that autoregressively you get the action from output and give it to the input. To summarize the general recipe, what you do is that you pick a pre-trained video diffusion model compared to VLA that you took a VLM. But now what you do is that you add an action module and train it such that you jointly optimize state action at the output of the model. But again, you need teleoperation data. That's the key. At runtime, again, you have the action, the last action in the output. You autoregressively put it as an input, and then you run it. And the rest, again, is the same. So corner cases, you pick more data, add it to the data set until it works. So the key challenge to me here is that you do teleoperation, which means that pretty much you didn't solve anything. You just show the robot exactly what actions are optimal, and then you do some behavioral cloning that is at least 40 years old. The only difference is that now we have higher capacity models, right? And these models really can absorb a lot of data, and that's the only difference than what we were doing 40 years ago on behavioral cloning. So to give you an idea of how this data is collected in the real world, here is a few examples, right? So one of the ways is that a human wear an exoskeleton, and then basically by looking at the end result of the robot basically performs the task, right? And you collect the data of the robot doing the task. A more fancy version is to use some augmented reality devices where you do not need to wear an exoskeleton, but now you can use a joystick to collect data, but the principle is the same. When you do it on a humanoid robot, this kind of teleoperation is more difficult. You cannot simply copy the action of human to the humanoid because the robot is underactuated, it can fall down, right? So here, for instance, Boston Dynamics, what they did is that they had a model predictive controller as the low-level control to make sure that the balance has a priority and the robot doesn't fall down while being close to the human motion. And finally, Unitree, for instance, did the same thing, but they used RL for instead of MPC, they use RL for a low-level control. I don't think that matters much. But as a basic, for a joke, normally I say that when people do this kind of stuff, the motto is something like this: in God we trust, all others must bring data. So the key is data. So this is something that you hear a lot these days. I do not 100% believe in that. I feel like this can take us really far. But there are issues that I'm going to talk about it at the end of my talk. But let's go with this motto at the moment. So for sure, teleoperation cannot provide you with the data that you require to basically train these models. So in my lab at the moment, what we are trying to do is that we are trying to find better ways to replace teleoperation in order to basically train this kind of models. So let's say the setting is something like this. You have the left side basically picture, you have a robot, you ask the robot to bring me this basket, the blue basket, right? And the goal is that the robot can figure out how to do it on the right. So it should reason about the environment. Okay, the basket is too high. What I need to do is that I need to take the box, put it there, step on top of it, and then grasp the basket, right? So this, I want it to be fully automated without me providing as a user anything to the robot, right? So basically that's the setting. So now how to generate data for this problem? So one of the easy ways actually, or easier ways, is that to retarget motion of the human, right? Human has solved most of the tasks we would like to basically the robot to do. So motion retargeting would be actually a very rich source of data. But this is different from teleoperation, because what we do is that we get only human video, right? We do not need to have a human doing full-time job teleoperating the robot. We can take unstructured videos from YouTube or anywhere, and then what we can do is that we can retarget to a humanoid robot. So here I assume that, we have some sort of demonstration, and I'll show that, with the motion retargeting, we can generate whole body trajectories, and then, what we can do is that we can build a tracking policy. Here we use RL, because RL is offline, is easier, in order to find the joint action. So this is one way if you have a lot of demonstrations, right? But for sure, some certain tasks, we do not have the reference for this system. And here what I would argue is that we can do something that is called motion discovery, right, for the cases that you do not have the reference. The problem is that motion discovery, I would say it's the holy grail of robotics. It's been very difficult because exploration in this large space of interaction and motion is super difficult. Hence, I will talk about how we can actually use LLMs to warm start this motion discovery such that we reduce the exploration burden on our algorithm. So this is our pipeline. Basically, the green box is my proposal to generate data. And once you generated data, now what you can do is that you can basically train what we call it the action head of the VLAs or the VAMs, basically. So here, but I also would argue that I would go for something like you have a generative policy that produce trajectories, predictive trajectories rather than controls, and then we have an RL controller. So I will show you later why keeping this structure is useful. And finally, what you can do is that you can also connect a pre-trained VLM in order to basically give you the sub-goals to make the generative policy to basically generate the motion and action for this. So this is the general pipeline. So what is the framework I like to use in order to look at the problem? So basically, the whole framework is optimal control, which was formalized by Richard Bellman, right? So basically, you have a system, xt plus 1 is the next state of the system, f is the nonlinear physics or dynamics or forward model of the board, xk is current state, uk is the current action, and wk is the disturbance. So since we do not have access to the full state of the system, so xk is not known, but what we have is that we have access to the observation. What we can do, we can build a belief state, of belief over the states, and the goal is to build or design this controller such that it maps the belief state to the control actions, right? So this is the control framework. And the main principle used is principle of optimality. Basically, in simple word, what it says is that if you have a problem you want to solve from time 0 to time n, if you have access to the optimal control of this problem, then this optimal control sequence is also optimal for any sub-problem that you consider in this problem. So this is very nice. Why? Because what you can do is that you can write down the problem as optimization only over the first control action at each state. If somebody gives you the value function or J star or optimal value function at the next state. So if somebody gives you that, you can solve this problem. So this is very nice. So this is how you use principle of optimality. But the problem is that this solving for globally optimal control policy is in general intractable, and this is what Richard Bellman called curse of dimensionality. So what it means is that as the dimension of your decisions increase from 1 dimension to 2, for instance, to 3, basically the size of possibility that you have to solve this problem grows exponentially with this dimension. So you can see this clearly in this picture, right? So if you have a point, you want to move it, if you move it only in the x direction, then you can discretize and you say, for instance, I have 10 possibility. But now if you make this x to x and y, then you have 10 times 10 possibility. Now consider that you bring this to the whole world. So then you become, for instance, a humanoid robot has 100 states at least I do not just consider the hands, then basically we will have 100 to the power of the number of discretization point for each dimension, the dimensionality of the problem. So this is the curse of dimensionality. So we cannot solve this optimization problem exactly, but what we do is that we resort to simplification or trying to approximate this problem. So this minimization problem we would like to solve is our continuous state, because Newtonian physics, right, is a continuous forward model of the world, if you want. Then this minimization is our continuous functions, but what we do is that normally we discretize our control space. So this is the first approximation we make. The second approximation is over the expected value, right? So expected value, we have it because WK is the disturbance in the system and it's a stochastic. So we need to average over all possibility of the uncertainty or lack of knowledge of the world. But here also what we can do, rather than computing this intractable expected value, we can resort to some simplification. For instance, we can use certainty equivalence, which says that you design the controller assuming that you know perfectly the state and the parameters of the robot and the world, which in practice is not true, but still it's a very good approximation that separates the problem of estimation or identification from the problem of control. There are other ways that you can approximate this expected value. And finally, and most importantly, the main or the most difficult thing is to approximate the optimal value function, right? So this is the most difficult part. And there are very different ways that we try to do that. For instance, we do problem approximation. We simplify our problem. For instance, if I'm talking about controlling a humanoid robot, right, I can just forget about all the flexibilities and consider the system to be rigid, which is not true in practice, but at least it helps me to approximate this value function. Or I can even go further and more simplify this problem, and I'll only consider the dynamics of center of mass. Or we can do something that is called model predictive control, which means that rather than solving the problem for the full horizon, you solve a short horizon problem. But what you do is that you apply the first action, get the state in the next step, and continue this process through a receding horizon fashion. And you can use something like neural network as a function approximation, for instance, that can also help you with finding tractable ways to find the optimal value function. And finding approximation to this problem is simply the fields of optimal control and reinforcement learning, right? So optimal control and reinforcement learning classically were developed in two different branches, but at some point people noticed that actually they are solving the same problem. The only difference that makes them a bit different in general in practice is that the optimal control, what you do is that you try to find the optimal trajectory of the system, while in reinforcement learning what you try to do is that you want to directly find the optimal policy, which is a function, right? So you want to find the function normally in reinforcement learning, the policy function, the relationship between state to control or observation to control. In optimal control, you find the optimal trajectory, and then you build a controller around this optimal trajectory. So this is the main difference. Otherwise, they are exactly solving the same problem, okay? So now, basically, I would like to use that optimal control framework and show you how we can solve each of the components that I showed you first, in order to first produce data and then train a generative policy and so on, right? So let's start with the motion discovery. This is something that is actually my interest, really. So if you actually look back in the primates, you can see that they are able to reason about the environment and use tools in order to achieve the task that they want. So these are motivation for me always for motion discovery, right? So for instance, if you see on the top left, you can see that the apes are building these boxes on top of each other to get to the banana, and then they can have food. On the top right, you can see that what the ape is trying to do is that it's trying to basically have a long stick, building a long stick in order to basically push the banana toward itself or drag it and then grasp it and eat it. And the bottom left is one of my the most interesting for me. So what the ape does is that it grasps this big stick, and then it uses it dynamic while it's falling down to go up and grasp the banana. So these are something super cool, and on the bottom right is also super interesting example, right? So what ape is trying to do here is, let me see, maybe I can wait. So what it does is that, it's trying to figure out how to remove this rope in order for door to start opening, and then it jumps on top of the door to basically move and grasp the banana. So if you wait for a second, you will see how it works, right? So you see that they are able actually to reason about the environment, right? And basically solve the task that they want. And this is exactly always my motivation, and I would argue that this is still an unsolved problem in the field. So let me formalize it a bit more here. So basically we would like to solve an optimal control problem. In order to do that, so basically we have a cost function, which is the sum of cost of each step into the future from time 0 to time t. We have a dynamics of the system shown by f, and then we have a set of constraints on the system, right? And then we want to bring the system from x0 to xe, and this is basically the most abstract way that I can write down this optimal control problem. So I can really put it like that, as that holistic, and try to solve it with some optimization. So this is an extremely big optimization problem. So you put all the constraints, like the robot has joint limits, you have everything. But the key constraint that makes this problem so difficult is something that is called complementarity constraint. And complementarity is there due to the contact that is not differentiable and gives rise to hybrid systems. So for instance, if you have an object that goes to starts making contact with the environment. Before contact, it had one basically dynamics. After contact, it's a different dynamic. So the dynamics of the system switches, and this gives rise to a hybrid system. But people tried to do some relaxation in the past and solve this problem holistically, which are very interesting works. So these are around 2012 to 2014. And since then, people have been trying to really run these things on the real robot. You see that recent papers are trying actually to do this. But to be honest, this problem is so difficult, in particular because of the contact dynamics, that basically when you relax it, it introduces a lot of bad local minima to the problem. And most of the optimization problem solvers we have are local and get stuck in bad local minimas. So they need a lot of tuning. And if you just look at the real world demonstrations that this line of work has shown, it seems that it's just very difficult problem. It's not really matched with the other approaches. Just to show you a bit further why contact is so difficult, here is a toy example. I took it from this very nice paper. So basically, when you have a system with complementarity as a constraint, right? So this is called mathematical programs with complementarity constraints, or MPCC. So on the left, for instance, if you have a sine function as a constraint in your problem, that's what you would have. But here what you can do is that you can start smoothing it, right? So you can either do it a relaxation, replace it by a blue, the sine function, or what you can do is that you can replace it by an inequality constraint, which is the shaded area. Both are fine, right? But now if you look at the second and third basically plot, you can see that, so let me just give you a bit of context. So the blue one is the set of optimal solutions, and basically the black one is the optimal solution that you could find analytically, because this is a very simple problem. So blue one is when you relax the problem so much. So sigma is the relaxation parameter. You see that the function values are so different, but the shape of functions are very similar, which means that you can basically approximate the gradients so well. But as you decrease this sigma, what happens is that you get closer and closer to the optimal solution, but you lose is the gradient, because your function now becomes so oscillatory, right? So this is a dichotomy here. So you want to make this relaxation so small to have a precise solution, but then you introduce a lot of local minima. And this is the main reason that most of these solvers, it's very difficult to basically tune this solver and make them work. An alternative solution is that you basically solve the problem with considering the contact as an integer problem in your optimization. So then it gives rise to a mixed integer problem, right? So I will explain this a bit later, because this is the framework we will be using in this paper, and this also has shown many successes in the past, and I would argue basically this is the way we would be looking at the problem. It makes more sense for me. So let's go a bit in more detail about this optimization problem. So we have a cost function we would like to minimize. Normally, the cost function is that, for instance, for a humanoid, we ask it to just clean the kitchen, right? So we want to have this as high level as possible. So X and U are continuous state and action of the system, and S and A that we added to the problem are called the symbolic state and action. For instance, you can say that make contact with the wall. This is the current state, is that you do not have contact with the wall. The next state is that you have contact with the wall, and then you see that there is a change in dynamics. So this is the first line of the constraint, which are at the symbol level. The inequality constraint can be something like, when you have when you are in contact with one part of the environment, at the same time you cannot establish another contact with another part, right? So you need to first release it such that you can make contact with the other parts. The second line of constraints are simply the continuous dynamics or forward dynamics or simulation and the constraints that you have. And again, you want to bring the system from x0 to xe, right? So this is the general optimization we are trying to solve. So to solve this problem, what we do is that we combine a search over symbols and a continuous trajectory optimization. So let's start explaining this. From left, the task, for instance, you ask the robot to bring the green box down, right? This is the only information you give to the robot. If you go to the second block from the left, here is a representation of the environment. So the starting point, you have a red box on the floor, the blue floor with a unilateral contact, green box with the platform unilateral contact, the feet contact with the blue floor, and the goal is to have the green box in contact with blue floor unilateral contact, right? So this is how you write the initial and final condition. And you just pass this to this huge optimization problem. And what this optimization problem does, it does a search over the discrete variables, which are, if you have symbolic variables like grass, push, and so on, it's going to be search over them. If you don't have it, it's a search over contact sequences, okay? Because I have two versions and I will discuss both of them. And then you pass this to constraint trajectory optimization that tries to basically see if this sequence is feasible, and then you iteratively go back and forth until you find the solution. Let's work out one example together. So let's start from the left. So one sequence of the symbolic action states would be: first, right hand will grasp the box, then right hand lift the box from the table, then place it on the ground and release it, right? So this is a sequence, for instance. So what it does, if you just look at the center of this graph, is that it just constrains some part of the robot and environment, right? For instance, when you say right hand grasp the box, the right hand is occupied, the object environment is also occupied. But left foot, right foot, left hand, or any other part of the body that you optimize for are free to move, right? And this is basically what we use and do a tree search over all possible combinations of this, right? And then pass it to the trajectory optimization to see if this proposal combination gives you a feasible solution or not. So let's see in practice how it works, right? So for instance, here are a few of this, this is called basically manipulation predicates. So this is, for instance, lift. This is a place. You can define this, or you may not define this. Later, I will show you how you can just skip this kind of semantic level symbols. And this is, for instance, release, right? So you could see how you can pick and place with that. Now, the thing that I said, so now if the manipulation proposal is that left hand grasp the box and then put it on the platform, right foot, right hand, if you have any other points, they are all free to be still optimized or searched over. And you can come up with this kind of basically is solution that make sure that it supports the body weight as well. So it can discover this kind of behavior while doing the search. Now, for instance, here we are showing two different scenarios. So here, what you ask the robot is that so what we want to do at the goal is that we want to have the two boxes on the right platform. That's it. We do not provide the robot with any other information. Initial condition, final condition. Of course, we provide it with the physics equations. And these are the sort of solutions that the robot come up with, right? So again, we did not predefine anything, and you can see that this optimization can find a diverse set of solutions that are different from each other, right? And this is nice because this is exactly what you need when you teleoperate the robot. You want to find all different ways that you can do a certain task, right? And this can be, you can see how this can be used as a data basically for training your robot. This is another task. What we ask the robot is to just go up the environment, and the robot decides that I can bring the box down, step on top of it, and go up, right? So this is one solution, but it can find other solutions as well, right? So here is another solution. It's the motion is different. Here is a bit of another minima. It didn't go up. Here is a more crazy solution, right? But all of them are solution to this problem. And in order to show you how, what kind of problems here we solve, here we put every single constraint of the problem inside the formulation, which means that here, if you simply remove the torque constraint from the set of constraints, this is the strategy the robot comes up with, right? So it says, I have enough torque, I can just jump on top of the platform. I do not need to bring the box down. Or it can do even more crazy stuff like this kind of behaviors, right? These are all physically, maybe it's not useful, but it's physically viable. So depending on the robot, if you have different torque limits, you can just put it there and you get different behaviors. And that's something that really you need to have in general. So recently, one of the key features or requirement for this kind of optimization is that you have a very efficient constraint trajectory optimization problem. And here is, for instance, a solver that Haiju in my group actually developed recently. So he named the solver Hippo, which is the top line, right? So you want to solve the left-hand side optimization problem, which is a constraint optimal control problem. And he fully benchmarked this with most of the existing or state-of-the-art methods, starting from FATRA, Bacados, Alligator, and so on. So you see in this table what are the underlying basically formulation, how the inequality and dynamics are taken into account, and so on. So I will not go into detail, but you need to solve this kind of continuous optimization problem once you have a sequence proposal. So here, for instance, he just benchmarked for a manipulation problem. You want to reach the goal, and then this is the basically outcome of the benchmark. So the time, the x-axis is the time to solve the problem. So what you do is that you sample the end effector desired end effector configuration, and then you want to see how fast you can solve this problem. And as you can see, the Hippo our solver can solve more problem in lower time. Here is a locomotion problem, which is more difficult, and you can see that other solvers can fully fail to solve it, and at the same time we have shown that we are more efficient. So the key component here is that so what Haiju did is that he tried to really implement interior point method efficiently on the robots, while other people mostly, or the existing board mostly, try to use it with augmented Lagrangian, and it seems that interior point method actually works better. But maybe, this is, I cannot go more into detail because it's very technical. Okay, so let's see how now we can use it. So this is, and given this solver that we have and the search that I talked about, here we said, okay, let's forget about any symbol that you want. So we do not want to define a grasp or push or so on. Symbols are not necessary, we said. And we directly optimize for the contact sequence, which means that which end effector at each point is in contact with which part of the environment. So if somebody gives you this contact sequence, it can be from a tree search as you see on the left, it can be from a user gives it, or it can be from a generative models, language models, or so on, right? So what we do here is that we basically, given a proposal of the contact plan, we can do a fast feasibility check to see if this contact plan is feasible or not, rather than solving the full problem at the start, because that's a very complex problem. So we define a nested structure in the problem that instead of directly solving a very complex problem, first we can do a kinematic sequence feasibility check that is quickly prune a lot of things that are not possible, and then we pass it to the trajectory optimization that solves the problem fully. So now here, let's see what kind of behaviors it can show. So the idea here is that you ask the robot that I want to have you standing on top of the platform, having both boxes in the hand, and this is the result of this basically optimization. So this is a super long horizon problem, and you see the motion is fully smooth because it respects fully the physics of the world, and it's somehow something that most probably you cannot actually teleoperate that, right? So this is the thing that we call motion discovery. And I should again emphasize here is that we did not do any heuristic here, right? So it's fully output of the optimization, this dynamically consistent trajectories. So you can do another, for instance, here is another problem. You ask the robot to be on top of these platforms with the object in hand. And here is another set of solutions that the optimizer can come up with. So it is important also to say that physics here is a constraint of our problem. So all of the physics constraints are satisfied. So it's fully physically realizable motion on the robot. So if you want to see more crazy motions, here are a set of more crazy motions. So on the right, you are asking the robot to just stay on the platform, and this is the motion it comes up with. On the left, you say, go on top of the platform while having the object in hand, and it comes up with this crazy motion. This is fully physically, correct, right? So most probably, if you just limit the torque constraint of some of the joints, it will not anymore find these solutions. So these are the crazy behaviors that without any demonstration or without any heuristic from human, the optimization can find. The only problem is that, this motion discovery problem is really a long search, because you need to basically search over a very, very combinatorial and large set of contact sequences. But here what we can do is that we can ask LLMs that have a very good understanding of the world because of the large amount of data they are trained on, to give you proposals of contact sequences, right? And here is the framework. So what we did in this paper is that we use LLM in the loop of the tree search. So there are this new wave of work in the LLMs where they do use LLM inside an evolutionary search for scientific discovery, right? So what you do is this, so you build an evolutionary search over programs. So here our program is simply a contact sequence. So on top you can see we have a text file which is a contact sequence. You pass it to this evolutionary LLM guided evolutionary search tree. What it does is that it builds a tree, right? And then what we do is that we pass this to our framework that checks the feasibility of this, and then we give feedback to this tree LLM guided evolutionary search, right? This is very important. So the feedback can be that, kinematically it's infeasible, or this constraint is violated, or any other kind of thing. And this can really help the LLM basically to quickly, or this evolutionary search, to quickly find the optimal solution over a few iterations. So the idea, again, is that this evolutionary contact plan discovery, it builds a sequence of contacts. We uses basically this our kinodynamic check and motion generation to give feedback to the LLM, and then if after a few iterations it can find the solution to this problem. And interestingly, we could find some problems and actually do it on the robot. Here, the only input we are giving to the robot, we want to have the box on the highest basically table, and this is the solution that it could find, and we run it on the robot. So this is purely output of the optimization. There is no heuristic. You do not at all tell the robot how to do it. And then it just could fully discover this motion, and then by an RL tracking controller, we tracked the desired trajectory. Here is another one. We tell the robot move forward, and you see that the whole way is blocked. So what it does, it needs to first remove the obstacle and then move on. And it can come up with this solution automatically. So again, we didn't tell the robot what to do. All the solution is emergent. Finally, here we ask the robot put the box on top of the table. And to show how robust this solution is, on one uncut video, what we do is that we put again the box under the table and ask the robot to do it again. You see, we randomly set the initial condition. And again, it achieves the task. So actually, it's a very robust pipeline that can really work on the robot. Okay, so here, until now, I showed you that with together with this kinodynamic trajectory optimization plus search and an LLM warm start, we can discover many different motions. But as I said at the start and motivated the problem, for many cases, actually, we have human videos doing the task, right? So it would be much easier if we simply try to retarget this motion to the robot. So basically, the idea is that, as you see in the block diagram, we have a human video. We build something that is called SMPL, which is the something from computer vision that is a body shape of a human, and then we retarget that to the robot, and then we track it by an RL controller normally. So the key problem that the current approaches have is that, you know, when they do the human to human retargeting, they only solve a kinematic problem, and this gives rise to a lot of geometric inaccuracy. For instance, the contact is not really valid. There is a distance, force at the distance, and this really make it difficult for RL to track this because the object will fall down and then it's not going to work. So what we introduce here is a dynamic refinement procedure, such that basically you, in one pass, you make the motion basically dynamically visible. So again, to see what kind of things we are trying to do, this is the human motion, right? You see that the foot is flying in the air, the robot is not making contact, and so on. And the output, we want to have a fully physically realizable trajectory. So it's not a trivial problem. The robot can fall down, the object can fall down. You know, there are a lot of constraints in the problem. So here what we propose to do is that we propose to do a sampling-based trajectory optimization instead of gradient, in order to make sure that you can basically satisfy all the physics constraints of the problem and collision constraints. So I'm assuming that you know basically this how this zero order optimization works. To give you just some context, is that what you do is that you sample desired actions, right? Roll out the system in parallel in simulation, the control actions, evaluate the cost, and then there is a weighted average that you do in order to get the next iteration. That's how zero order optimization works. For instance, MPPI, CEM, CMAES, and so on. But here the problem is that, you know, this zero order optimization do not work well when you have a long horizon problem. And here is our contribution. So we defined a way that you can basically break down this long horizon problem. Let's say you want to solve the retargeting problem from 0 to t. Our sampling-based trajectory optimization first starts to solve the problem in a short horizon. And then what it does is that it increases the horizon and add the solution of the first part as a warm start for the second part, and continue this until it solves the full problem, right? So I will show you in the next slide how useful this is. And if you just directly try to solve the full problem at the start with the sampling-based trajectory optimization, how this long horizon problem fails to be solved. And also what we noticed later is that actually at the later stage of the optimization, you do not need to solve the full horizon, because the first parts of the action remains fixed. So here we defined an alternative, which is SPTO skip. So what you do is that after some time you see that the earlier action or first actions are not optimized anymore, remains fixed. So you do not optimize on them anymore. And then by just sliding the window of your optimization, you basically solve the problem. And this is much more efficient than the first version. Okay. So let's see what happens, right? So this is the kinematic retargeted motion. And you see that how bad the motion is. If you just pass this to RL, it fails. Now this is the output of our SPTO framework. So the contact is fully feasible, the physics is correct. And here you can see how the iterations work. So sequentially, it's increasing the size of the horizon, and warm start the solution of the next problem from the previous one. And this is the final solution. So you see that the robot could solve a very long horizon problem, actually. And here we compare with two baselines. So one of the baseline on top is a sampling-based MPC, which is a state-of-the-art. So sampling-based MPC, you solve a receding horizon, fixed horizon problem. And this fails because, at some point, if the robot makes a mistake at the start, then it cannot really follow the desired trajectory anymore. And in the bottom, we did it with just one full, trajectory optimization for the full horizon. And you see how both of them fail for the same task. Okay, so this basically we show that we need this incrementally increasing the horizon of the problem. Okay, then we applied this to existing data sets, and you can see that we can generate a lot of different motions for the robot. Here, for instance, to do moving box with different strategies. And this is fully physically realizable, right? And now the other nice thing or side effect of this algorithm is that now what you can do is that you can just, because you're running the sampling-based simulation, you can change the size, the mass, the geometry of the object and scale the data generation to a large body, right? You can see that the same demonstration, one single human demonstration that we have, it can be scaled to many different objects, many different shapes, many different masses. And some interesting behavior is that, here, for instance, the robot, was tasked to do, this was something like the demonstration, but if you reduce the size of the object so much, this is the motion that the optimizer would come up with. Still, it solves the task, right? But since the object is very small, it came up with this idea that, okay, I can use my foot actually to shoot it and then grasp it. So this kind of thing still can be emerged from this optimization problem. And then we showed this on the robot on all these different kind of settings. Okay, we did also an extensive ablation. So basically, SBTO skip, the first line is the algorithm, the final algorithm we proposed, and a spider in the bottom is the state-of-the-art based on sampling-based MPC. You can see that the success rate is increased by a factor of 2. So basically, we took a data set with a large amount of basically demonstration, and we were able to retarget 76.8% of that to the robot. Note that those motions are from human, right? Which means that retargeting may not be successful because robot has a different morphology, different constraints, and so on. We also showed that basically our motions are generated motions are much more smoother, and so we defined a smoothness metric and showed that basically the lower smoothness metric the better. And in terms of the counterintuitive thing is that we have shown that actually we can be better in terms of computational efficiency as well, in terms compared to the sampling-based MPC, and with a better error. And now we also compared for the downstream RL tracking controller how better this is. So basically what we showed is that our approach can improve the tracking. So let's say you have 100% retargeted trajectories. Our algorithm can, the RL can track 95.84 of them, while for instance, state of the art, they have something like 78%. Okay, good. So I think I'm done at this point with the data generation. With these techniques that I talked about, you can generate really a large amount of data, right? And this is without with zero teleoperation. So this is very important. So you can start building your generative policy with zero teleoperation. Of course, if you have teleoperation, you can use this such that you increase the amount of data. But still, we are showing that in extreme cases, without any training data of teleoperation, still we can build our general purpose robot. So now, basically, we'll see how this data can be used in order to build this generative policy. So here is a pick and place, basically, motion. So these are the set of trajectories we give you. The ghosted robot are the, some other trajectories. This is the first-person view of the robot doing the same task, right? And this is what the robot do in practice. Again, here we did not use really the the vision part. We just only rolled out the trajectory and tracked it with RL. Okay, but I do not see that being a big bottleneck. So this is the early results of our basically diffusion policy. Now what you can do is that you can run the algorithm. Basically, so this is the output of diffusion policy given different goal conditions of the object. And you can see that the robot is able to bring the object to different places. Okay, now what we did as well is that, so we generated this generative policy, we trained this generative policy, which is actually a diffusion policy. It generates a trajectory, desired whole body trajectory for you, and then we used our pre-trained RL tracking and then just put them together. And here is the result. So you can see that the ghosted version of the robot is the output of the diffusion policy that gives you desired trajectory, and then the solid one is the real robot trajectory. And now what we are trying to do actually is that we are trying to fine-tune this. So now that we have these two models separate, what we can do is that we can leverage the recent advances in fine-tuning large models in order to fine-tune these two models together. So this is what we are trying to do at the moment. Okay, to summarize what I've talked about until now is that so I showed you how we can use different ways in order to generate data for our humanoid local manipulation problem. Either you can do retargeting from videos, or you can do motion discovery if you do not have a reference, but still LLMs can be very useful to in order to improve the search efficiency. You generate data and then you train a generative policy in order to basically send you action to the robot. The thing that also you can add to it, now you can make it, go one step higher and add a pre-trained VLM to it. And then basically you give the VLM the representation of the environment. It gives you some sub-goals, first grasp this, put it there, and so on. And then the generative policy translates that into action. So that's a general path I see, or we are working on in order to build a generalist humanoid robot, right? So this, to me, is a scalable path to the future. But do I mean that actually it's all about scaling to have really a general purpose humanoid? So here is the place that I'm gonna push back a bit. Actually not. The real world is super complex, right? Which means that things can go wrong. And as soon as things goes wrong like this, then basically our trained policy is no longer able to handle this situation, because you go quickly out of distribution of your data, and we know that this neural networks cannot do anything when you go out of distribution, right? So this is the main thing that makes robotics difficult, and it's important that we have some way to basically, first of all, handle safety, and second of all, be able to learn with from the failures in the real world. So here is again the pushback. While we can really push it forward with the current generative policies and so on, and the humanoid general purpose robots, safety is a critical issue, and we are far from solving it. So in order to show you how far we are from solving this safety problem, I try to compare it with autonomous driving or self-driving cars, right? So I remember 2015, people were saying, okay, self-driving cars are there in our cities in 2 years, right? And still, we are in the year of 2026, and we do not see them, right? And I would argue the main reason still is safety. So this is a very safety critical problem. You do not want to make any mistake, because this is very fatal, the mistake that you make. Now, if you just draw a parallel to a humanoid robot, while the basically accidents or failures are not so fatal like autonomous driving, but the space of failures you can make is much larger, right? For instance, you can see that a car is just a unicycle moving on inside a lane. A humanoid robot should work in any surface, in any environment, and then it should manipulate, locomote, and so on, right? Just to make this more concrete, I try to categorize all types of safety concerns that we have and we need to take into account in the problem. So there are 5 main categories that I could basically come up with. I'm not saying this is complete, but this is something that I could think of. So the first one is collision avoidance. So basically, when you have a humanoid robot or you have an autonomous car, you want to avoid colliding with a wall, for instance, or other cars or other people, right? So this is a similar problem, but still the humanoid one are much more complex, because human is an articulated system. So you have arms, you have legs, and so on, and the collision avoidance problem is much more difficult than a car that is like a box, right? The low-level safety means that the low-level command you send to your actuators should be safe, which means that if there is a failure, things don't go wrong, right? So in the cars, you do not have so many actuators, so you have a throttle and brake if you want. And a robot, you have many actuators on each joint and many sensors, which means that if some of them or one of them even goes wrong, the whole system might collapse. Semantic safety is something that is quite difficult actually to rigorously study, but still I would argue that it's much more difficult for a humanoid robot, because cars are much limited. They only need to move on a street, and they need to simply avoid moving to or running to objects or other entities. For a humanoid, actually you want sometimes to go and grasp something, right? And then you don't know if the thing that you grasp is semantically graspable or it's something that is dangerous, right? So it's a much more complex problem. The fourth one, which is fall avoidance, actually doesn't exist in autonomous driving. So autonomous driving, the cars are really a stable system. In very, very rare cases, they can T-power. While you can see that humanoids are very easily fall down, and things can very easily go wrong in terms of the object they are manipulating. And finally, the last one to me is the most critical one, interaction safety. So cars, in order to basically achieve what they want to achieve, they only need to avoid making contact with the environment. However, locomotion and manipulation are intentionally making contact with the environment, right? So you need to have this making and breaking contact with the environment in order to achieve the desired task that you have. And this is very difficult, because in order to, for instance, grasp an object, you cannot press it too much because you can break it. You cannot press it too little because the object falls down. There is only a small, very, very small set of forces that can be applied. And this is such a difficult problem, right? So I hope with this picture I could show you that, how far we are from really using humanoid robots in our daily lives, right? So safety will be really a critical issue. Still, I would argue that we can really push to a very high reliability with more and more data, but safety will remain there, right? So if you are okay with the right picture, that if you leave the robot at home to do cooking or cleaning for you, and when you come back you see these pictures, then it's fine. I think in few years we can have something similar to this. But this is not something that you can have it at home, right? So, and given the situation we had with the autonomous self-driving car, which is, I would argue that 10 years ago the technology was there, still we do not have them. Humanoids will take even more, because as I showed you, the safety problem is much more difficult. But still, I want to just discuss a bit the works we have been doing on the safety aspect of the problem. So the first one is the work we did in order to basically do collision avoidance and fall avoidance for a navigation, robot navigation problem or quadruped navigation problem. The thing is that the whole framework that we are using, and I believe the best way to do the safety or handle the safety to me is using predictive filters. What does it mean? It means that you have a pre-trained policy, you trained it with imitation learning or reinforcement learning, it doesn't matter. What you do is that now what happens in the real world is that you go out of distribution of your training data. So what does it mean? It means that if you just predict under current policy forward the state of the world and yourself, you will violate some constraints. For instance, constraints of collision avoidance. But here what we can do still is that we can use model predictive control. Here I mean sampling based, because they can explore much better, in order to basically, in case that under prediction some constraints are violated, we can just give alternatives if possible, right? Within the compute budget, if we can find an alternative. And this is we call it model predictive shielding. And the idea again is that here in this problem we wrote down this safety at the level of contact, but you can do it at each level, at the full body level or anything. So here, for instance, is an example that we did something that we call it a contact condition policy. So let's say the goal that you have is that you want to track a desired behavior, which is a contact plan, right? So this is the work we did, and then in this work we showed that when you train an RL, if you just condition them on the contact plan, you can have better generalization, and you can have a single policy that can do all different set of contact switches. So we assume now that we have trained this contact condition policy in simulation to, for instance, walk on a flat terrain. Now, in reality, what happens is that there are some obstacles that you didn't see it during training appears. If you just roll out your RL, what happens is that you will hit it and nothing happen, and the robot will not do anything better. Here, what we are doing is that we roll out into the future, see if the collision constraints are violated. If they are violated, the MPC take over, give you alternative contact plans, and then you go move around the object. But again, this action of the MPC does not have to be on contact plan. It can be in the joint space actions. Here, because our computation was limited, we worked on this abstract level of contact. So you see that under the prediction forward, if there is no collision, what you do is that you continue your plan. If there is a collision, you just run the sampling-based MPC to get an alternative. And here are some experiments. Again, you can see that the robot is changing its foot location in real time. It's not trained on any of this environment, and it can avoid basically this object. So in simulation, the RL is only trained to move in different directions. And now with this shielding or safety filter, predictive safety filter, we can have collision-free motions with the obstacles that we do not want to collide. So in the previous work here, what I showed is that we use just a standard sampling-based optimization like MPPI plus CEM, which are inherently actually local methods. Something that I recently came across, and there is an advancement in optimization theory, is some global optimization that we recently came across and started using it. So Zhudang, my postdoc, has been working on this. So consensus-based optimization is, again, a particle-based optimization. that basically tries to have, so basically in order to explain it, I think it's easier if you look at this visualization. So this is your cost landscape, right? So the blue star is your global optima and the dots, orange dots are local optima. So you initialize your particles of your sampling based optimization. So if you have any existing methods that are local, what happens is that they most probably will converge to one of these local optima. However, what consensus-based optimization does is that it forms at each iteration a consensus point. Here is red, right? So at each point, it does a weighted average, exponential weighted average, find the red cross, which is the consensus point. However, there is a diffusion term that is added to this consensus, basically this dynamics of the search, where the red point over time converges to the global optima. So this is the visualization of how it works. So in special cases, this optimization will go to something that, you call it, people call it MPPI. So for instance, in the first equation, if you put lambda times delta R equal to 1, okay, and then, you do the right diffusion term, you change it a bit, you recover the MPPI control law. But this is much more general, and actually people have shown that in the limit, it's guaranteed to converge to global optima, while none of the existing methods, the other existing methods, have this guarantee. And then we tried it on multiple complex, problems. So this is the first problem. We want to go from the red, from the black square to the blue point inside this container, but the environment is highly limited. This is a very long horizon problem, which is very difficult to solve. It seems very easy, but since it's long horizon, it's very difficult. And you can see on the right that actually MPPI and CMA both fail to solve the problem. However, CBO is finding the solution to this problem. The second example was a double pendulum problem, which is highly underactuated. Here, CMA could, to some extent, solve the problem, but MPPI again failed. And finally, we showed that actually this problem can be solved for even scale it to the humanoid problem. So here, the ghosted version of the humanoid is the goal we want to be in. We do not provide it any information to it. We just pass it to a particle-based optimization, and we wanted to find a strategy to reach to the goal. Of course, this high-dimensional problem, the existing like CMA and MPPI fails. However, CBO could find a solution, right? Still, you need to give it time to do the exploration, but it will converge to the solution. So this is very exciting to me. Why? Because now we can use a better exploration strategy in the sampling base for safety. So here, if you see here, I showed you very simple visualization of how MPPI compared to, for instance, CBO work. So when you do MPPI, you have a starting distribution. You sample from that, from the mean with some noise. You get some trajectory, and then you average. Again, sample around this mean and average. So that's why I'm calling it local method. What CBO does, it just considers these particles that moves on a stochastic process or Langevin dynamics. And then this differential equation, which moves all the particles, are guaranteed to basically converge to the consensus. The consensus point of these particles will converge to the global optima. So let's see what does it mean, or what it implies actually, this thing. So let's say on the left, the idea was that we trained the robot in order to grasp the object and just bring it up. There was no table in the simulation. But of course, if you just, in practice, you run it in the existence of the table, it will fail. Now we did this, the model predictive safety filter or shielding, and here is what MPPI comes up with. Still, it can stabilize the system, but the object hits the constraint, and it could not really deviate so much from the plan. That's why it could basically violate the constraint. However, if you look at CBO, it comes up actually with an interesting behavior. It just grasps the box with its between the both feet, and then it bring it up, and there is no collision between the box and the environment. So these early results actually gives me hope that we can use better sampling-based algorithm that can do better exploration to handle better out-of-distribution scenarios in real time, given that we have enough compute in real time. Finally, I want to also talk about a small thing we did, work we did on the interaction safety as I said, to me, this is the most difficult problem in the safety level. So, for instance, if you see on the schematic figure A and B, if you want to do manipulation, for instance, grasping an object, normally the position of this object is not known, it's uncertain, and then you need to make sure to have a strategy that handles this uncertainty. Also, when you are doing walking, the environment, you only have an approximation of this and it's uncertain. So normally when we solve this problem, trajectory optimization, we just use deterministic problem, because the stochastic problems gives rise to combinatorial problems. But here what we showed that actually we can modify the optimal control problem and define some branching phase, where you consider all possible contacts that can happen inside the uncertainty set, and then you branch at those points the optimal control problem. However, you force them to come back to a consensus, and then you solve the problem to the end, right? So the brute force version would be that you branch and then you run them, all of them in parallel until the end, but this is computationally very difficult. So this simplification enables us to basically solve, for instance, this egg catching problem. So on the left, we solve the deterministic problem. On the right, we solve our branching and stochastic optimal control problem. In terms of a strategy, if you just focus on the videos, you can see on the right, the safe one that takes into account the uncertainty first goes up, and then with the egg comes down, and this helps you to reduce the impact such that you can grasp, basically catch the egg. On the left, it doesn't do that because it doesn't know the uncertainty, so it says, okay, I can't catch it exactly at the right time. However, because of the error, it may not happen, so it can lose catching the egg. So this is, for instance, one way that we try to handle the uncertainty in the contact, but this is a very difficult problem, at the same time very exciting for us to look into. Good, I think I'm good with the time, so let me just summarize what I talked about today. I think VLAs or word action models are very powerful, but the key is data, if we assume that we want to move them to very good performance. I showed you that the different diversity-driven trajectory optimization can actually generate a lot of data without any human teleoperation. As I showed you, human-to-humanoid retargeting using unstructured videos are an important source of data that we can use. Also, one thing that I emphasize is that when you are training a neural network or a generative model, the representation is very important. And I think adding inductive biases, for instance, separating planning, so you can have a generative model that generates trajectory and a tracking RL controller, or for instance using contact as a goal, this can help with the generalization. And finally, safety, especially out of distribution cases, is essential to bring the robots to the end. And here is what makes me not super optimistic that we'll see humanoid robots in a few years in our homes, mainly because of the safety. At the same time, I think very deeply about the ethical question in robotics and AI. So I really recommend you take a look at this very good paper called Ethics of Artificial Intelligence and Robotics. There are many issues that are actually dedicated, basically specific to robotics. For instance, as in particular, autonomous weapons. If you have automation, the unemployment can be a problem, and the physical human-robot interaction or social one, we need to make sure things don't go wrong. So we wrote a survey paper last year on the learning-based legal locomotion, and there actually we discussed the societal aspects and ethical aspects of legacy systems and human-robot in general. Also, I'm a member of the IEEE Technical Committee on Responsible Research and Innovation in Robotics and Automation, something that has started very recently, so I'm really looking forward into it to see how we can really guide this line of research and make sure that, safeguard it and make sure that it doesn't go wrong. And at the end, I would like to thank my team. It was all work of them that I discussed today, and I would like also to thank our sponsors. And I'm happy to take any question.